Hi, I'm Paul Battaglia, and this is section 2.6, Rational Functions. In section 2.6, we make a sharp turn away from polynomial functions. The essential idea of this section is to get students to graph rational functions. But before we do this, we need to rediscover a domain, and we need to talk about other characteristics that play into the graph, such as asymptotes. I'm joined by Gabe and Brittany. And Brittany, I know you want to talk a little bit about vertical asymptotes, right?
Correct. In my class, the first thing I like to focus on after domain is to focus on the removable and non-removable discontinuities.
Right.
So the removable ones being, as I would tell my class, the holes in the graph, while the non-removable being the vertical asymptotes, where the denominator is equal to 0.
Right. And I think, one of the things that sometimes my students forget even is that there still is that domain restriction on the removable ones, So we still have to have that value excluded from the domain, right? And then Gabe, I know you do a lot of work with horizontal asymptotes with your class.
So something that I like to do when discussing horizontal asymptotes is I like to just start by having students look at 3 examples. So the graph of something like y equals 1, or any constant, y equals x, and y equals 1 over x. Because as we know, these are going to sort of lead us into the 3 possible cases that we have when talking about these horizontal asymptotes.
Right.
So then, when we're dealing with these rational functions, I like to have students just write down a new function where they take the leading term of the numerator divided by the leading term of the denominator and simplify this. And what happens here is that the end behavior of this new function is going to have the same end behavior as our original rational function. So this ties into this idea of these horizontal asymptotes, where we have the 3 cases. If the degree of the numerator is greater than the degree of the denominator, well, then our function can either increase to infinity or decrease to negative infinity as x grows without bound.
Correct.
We have the case where they're equal, so the degree of the numerator equals the degree of the denominator. Here, the horizontal asymptote will just be a constant. And then in the 3rd case, if the degree of the numerator is less than the degree of the denominator, well, what will happen here is that our horizontal asymptote will be y equals 0.
And I think sometimes what we see students struggle with a little bit is this idea of why is only the leading coefficient in play here? What happened to all these other terms? And so what I like to talk to my students about is I kind of have them imagine some things. I say, imagine if your function was 7x cubed plus 5x minus 1. Now, if I were to give you $1 million and then cube it, right, you'd be really excited. And then if I asked you to borrow $1, like that minus 1 at the end, you wouldn't really care because you have $1 million cubed, So I think that gives them a good idea of why that leading term is so powerful and plays into the behavior, of the function. So then obviously, like we said before, the next piece of the puzzle is let's take all of this information, domain, asymptotes, and let's make a graph out of this, right? But the reality is there's more to the graph than just those things, right? So Brittany, what do you like your students to also include when graphing?
I like them to include the x-intercepts, the y-intercepts, and then obviously the asymptotes.
Right, okay. And Gabe, how about you? Is there anything else you want them to put on there?
I ask my students to plot points in between either the x-intercepts and asymptotes or 2 consecutive x-intercepts.
More accuracy then, right?
Yeah, because that gives them a better idea of what the graph might look like.
Great. I hope these tips have been helpful to you and you find much success in section 2.6.